Hello, Fred. How are you?
Good morning, Mark. How are you?
Good, good. Now, for our listeners, I'll say that you're in Sydney, Nova Scotia, and for people outside of Canada, Sydney was the location, the previous location of the Sydney tar ponds. There was a very large remediation there that spanned probably a 7 or 8 year period, including the assessment component of that. And now the site is all cleaned up. It's been covered over, and I haven't been there in a couple of years, but I hear that there's a very nice park built on top of the site, and there's going to be an Aerosmith concert there in the near future. Are you going to that, Fred?
No, but it's set up for this weekend, and they're already building all the structures on the park to get to accommodate the Aerosmith.
Oh, there you go. And both you and I worked a lot on that Sydney Tar Ponds project, on the assessment of the initial problem and the remediation. And it's nice to see that Aerosmith will get to enjoy our handiwork.
Yeah, right.
So, Fred, I'm looking forward to your talk today. It's up here on the screen now, and please continue. Go ahead.
All righty. Well, good day, folks. Thank you very much for dropping in to take a look at this talk. When we're going to be talking about Cape Breton's changing climate and its implications for its freshwater resources. And as you'll see on the screen here, this satellite image. Cape Breton is outlined in green. It's an island at the northern tip of the province of Nova Scotia on the east coast of Canada, and it covers roughly about 12,000 square kilometers, which includes the large inland sea in the middle of the island. Okay, now as we go through the talk, I've found that it's important to get a good feeling for field conditions. It really helps you understand the terrain we're going to be dealing with and some of the difficulties we're going to be showing in terms of how we look at the water resources and how they're going to be impacted by climate. So you're going to be seeing a lot of field shots within different parts of Cape Breton, and I thought this one was appropriate as our table of contents slide, because we are going to be looking at rising sea level and its implications for streams and groundwater. And this is on the west coast of Cape Breton in the Cape Breton Highlands National Park at a place called Pillar Rock, as you can see in the background there, under a good storm surge. Alrighty, we're going to divide the talk into 3 different areas. First, we're going to talk about known unknowns. Then we're going to talk about how is our climate changing. And finally, what do we know about its impact on our freshwater resources? Now, in addition, as we go through the talk, I'm going to be using a number of different satellite images to help you understand some of the concepts. Rather than discussing the origin of each one of the satellite images as we go along, I thought I'd just throw them up on the screen early here. Global views will be coming from NASA's GOES East satellite. Intermediate scale, sort of the Atlantic provinces region, will come from NASA's Terra and Aqua satellites from MODIS imagery. And finally, when we get down to Cape Breton on the right there, we're going to be using Landsat imagery. All right, well, let's start off with known unknowns. Or what do we know that we don't know? Okay, the key concept here is that Cape Breton lies in an extremely complicated hydrologic setting, which means it's very difficult to begin to understand how climate is changing and therefore what its impacts are going to be. This particular shot is a digital terrain image, so the greens and browns are topography above sea level, with the darker browns being the higher elevations. All the blues are topography below sea level, and the darker the blues, the deeper the water, and you can see the continental shelf here. Cape Breton is here. So, in terms of the complexity created by the ocean, we have the cold Labrador Current coming down from the north, meeting the warm Gulf Stream just offshore. As well, on the east coast, or the west coast, we have the Gulf of St. Lawrence estuary, so warm, sort of brackish water conditions. And this is the estuary for the 15th largest drainage basin of the world. And those warm estuarine conditions meet the cold North Atlantic in the Cabot Straits here between Cape Breton and Newfoundland. In terms of climate, just keep in mind that here The northeast U.S. and the Atlantic provinces of Canada lie on sort of the outflow of all the winds crossing the North American continent. So we're sort of on the tailpipe of everything that gets put up into the atmosphere, and it all comes across us. Then over in the North Atlantic, we have the North Atlantic Oscillation, which causes changes in the jet stream and where the storm tracks go. And finally, we lie in that same position where a lot of the hurricanes move as they come up out of the Caribbean. So we've got a lot of factors and forcings on our climate. Coupled with that, we have a pretty complicated terrain on Cape Breton. That will vary between here. This is crystalline bedrock on the Cape Breton Highlands, a vast peneplain region, very little overburden, well-fractured crystalline bedrock, both plutonic and metasediments, volcanics. We also have, when we get into the higher areas of the Highland Plateau, we have the vast taiga forest region with quite a large number of wetlands. Incised into that Highland Plateau, we have numerous canyons, such as the Cheticamp River Canyon here. And some of these canyons, as exemplified here, are deep, V-shaped, down about 500 meters in depth. But we also have broad-scale canyons, like the Northeast Marguerite here, where broad alluvial sand and gravel, flat U-shaped canyons. We have steep transition slopes going between the Highland Plateau and the lowlands, as shown here on Kelly's Mountain. Steep transition slopes, hydraulically active fault zones, talus cones, and abandoned alluvial fans from Pleistocene era, and a good hardwood boreal forest, a hardwood Acadian forest. However, sometimes those steep transition slopes go straight down to the sea. This is the west coast of the Cape Breton Highlands Park, Skyline Trail, for those of you who may have been on it, Cabot Trail over here on the right. Along the southeast coast of the island, we also have crystalline bedrock, mostly volcanics, a few plutonics. But here, instead of being at elevations of 400 to 500 meters, they're right down at sea level. And we have a thick till cover. This is Louisbourg, Fortress Louisbourg, that you may have visited at some point. And also along that coast, we have a shoreline of submergence. So we have vast baymouth bars and large estuaries. And this is the Gabarus Wilderness area. We also have vast lowlands, such as here in the Sydney coalfield, with a variety of sedimentary rocks, sandstones, siltstones, shales, mudstones, and economic coal seams, all dipping offshore. And also embedded in the very parts of those lowlands, we have hydraulically active karst regions. So we have a wide variety of terrain. Here you're looking at Cape Smoky, off to the northern part of the highlands. Ingonish is here. Amidst all of that complexity between the ocean, the climate, and the terrain, the difficult part for us is that we have a low level of monitoring and research. So it becomes even more difficult to try and understand how our climate is changing and what the impacts will be. So perhaps this particular phrase says it all. In science, we commonly think that quantitative precision is our great strength, but before measurements can be meaningful, they must be directed to the right things. And even in science, finding these things, for example, asking the right questions, is the major achievement. So, in that regard, as we proceed, we'll be talking about what we know, the known knowns. But also a large measure of what I've been doing today is trying to figure out what are the known unknowns. What do we know that we don't know? And those are asking the right questions that could direct future research. Okay, so much for the first phase of the talk. Now let's go to the next one. So exactly how is our climate changing? Well, certainly when you talk about climate change, the first indication people have are this is man-made. I've tended to say, how is our climate changing? So I'm not going to get into the debate of whether our climate is changing because of man or because of its nature, natural rhythms, or it's both. We'll leave that for others to deal with. The fact is it is changing. What are the causes? That's for someone else to deal with. The first thing people think about when we talk about changing climate is air temperature, and certainly this is NASA's summary of 2012 global temperature anomalies. So you can see that we're up in here, and we're in the area of +2 to +4. So certainly in a global scale, we are seeing increased air temperatures. If you look at a variety of different people who have tried to work out past histories of climate, they've come up with this sequence of temperature from 1880 to the present. We are fortunate enough in Cape Breton that we do have one long-term climate station based in Sydney, which records go back to 1895. If you compare what we're seeing here on the island with what those 4 other research units came up with, you can see we do have the lows in the early 1900s, a peak in the 40s, drops down into the sort of late 70s, early 80s, and then we've been seeing this increased trend here. So what we're seeing in Cape Breton seems to agree with what they're seeing other areas. We get into precipitation and things start to go off the rails because that doesn't quite agree with what people think should be happening. So we plotted up the Sydney-based data. This is total annual precipitation from 1,000 to 2,400 millimeters per year here, and from 1895 to present. And if we plot up the total annual precipitation each year, this is what we see. A lot of variability. If you look at what climatologists think about this, they are looking out in a much larger time scale than we would normally do as hydrogeologists and hydrologists. They use 30-year normals, which means they take a 30-year period, take the average, skip 10 years, take the next 30-year period, take the average, skip 10 years. So this is what they're seeing using the Sydney data. So they're seeing this increase in precipitation, and the long-term trend for Sydney is increased precipitation out to 2100. However, you can see there is some fluctuation in here. So I've fiddled around with statistics, and what I found is if you use a running 10-year mean, this is what you get. And so we're starting to pick out decadal scale cycles going on. So in the late 40s, early 50s, we had low total annual precipitation. It peaked in around the late 70s, early 80s, and it's been going down ever since. So for hydrology and hydrogeology, sometimes these 30-year sequences are going to be more important than maybe the climatological 100-year view. Another aspect of precipitation that we have to look at are short duration intense storms. So the general consensus is that because of these big thunderstorms, and this is a big thunderstorm coming in over the central part of Cape Breton last year, consensus is that what was a 1 in a 100-year storm, by 2100 will become a 1 in 50-year storm, so halving the currents interval. But that's for the short duration, high intensity storms. But we don't tend to see those very much in Cape Breton. So if you use the Sydney data, what I've done is to look at the number of days per year of thunderstorm activities between 57 and 2012, and this is what you get. We have a low number of days, between 5 and 15 days per year. There may be a slight increase in here, but really no major significant increase in thunderstorm activities. And if you look at the real critical thunderstorms that give hail, this is what you get. No big change, very few, usually 0 and anywhere from 1 to maybe 4 days a year. So we don't tend to get those big intense precipitation events that everybody says is going to increase. But what we do get are long duration, low intensity events. So we have a nor'easter season that runs between October of one year to April of the next year. But we also have a hurricane season that runs from June to November. And you can see there's an overlap here between the nor'easter season and the hurricane season. So these, as I said, are long duration, low intensity events. So it rains, and it rains, and it rains, and it rains, which totally alters how we deal with runoff. Ground surface gets saturated, more runoff for a given amount of rainfall, and enhances groundwater recharge. And generally in Sydney, we find most of our hurricane season as we peak in August, primarily in September. But if we look at long-term trends, 10-year periods, 1901 to 1910, 1911 to 1920, this was created by Environment Canada. We look at the number of hurricanes. You can see that it actually peaked back in the 30s and 40s. It's fluctuated, a little bit of peak in 1991 to 2000. I haven't seen what the next 10 years are. There's no big increase in those events as yet. The other interesting is the time scale again. This is a major flood event that happened on the northeast Margaree River, took out the road. And as hydrogeologists and hydrologists is something that we have to again think about in terms of how we view changing precipitation and how climatologists do. So the green is the HAITA graph, so it's hourly precipitation over about a month's time from October 2000 to the end of mid-November 2000. And the blue is stream flow that's reacted to that event. Now, the problem I had when looking at this is that if you look at the intensity, duration, frequency curves that Environment Canada turns out, the maximum duration is for 24 hours. But because we have these long duration events, we need to understand what goes on way past 24 hours. So I actually had to go to Environment Canada and ask them to expand the intensity, duration, frequency curves out for 30 days. And when you do that, in this case, this particular storm was a 1 in a 100-year storm event for 6 and 12-hour durations. But that's as much as you would have been able to get from the initial 24-hour duration stuff. So when I asked them to extend it, this particular storm then became a 1 in 50-year storm for a 2-day duration, and all this became a 1 in a 100-year storm for a 5 to 30-day duration. So this really starts sticking in enhancing groundwater recharge, enhancing surface water runoff. So for hydrologists and hydrogeologists, I'd suggest that you really want to expand that those IDF curves so we can begin to understand how these are changing, not just the short duration events. Another aspect, certainly of precipitation, is snowfall. Here we're standing on Cape Smoking, looking back to Sydney in the background. I've used this because it indicates we have lowland regions in Cape Breton, but also highland plateau regions. This is the total amount of snowfall using that 10-year running mean for Sydney in a lowland site. You can see we had a low in the 40s, peaked in the 60s, little peak in the 80s, but it's been going down ever since. That would tend to make sense in terms of what climatologists are saying. We're warming up. We should get less snowfall each year. So in the lowland area, that seems to make sense. Now you go into the highland area, which is a totally different ballgame. Here you can see that we have a major snow belt in the Cape Breton Highlands here. The Sydney station, the lowland station, was over here. So you can see by March we've lost most of the snowpack in the lowlands. By April, you can really see the results of the snowpack left in here. The reason is interesting in this, and that is, this is Cape Breton, March 2003. The reason for the snowpack is that in the winter months, early winters, November, December, early January, the winds come across the Gulf, pick up water before the ice gets here, hits the highlands, rises up orographic precipitation, drops it on the highlands. But back in in 2003, the ice pack builds in by early February, so it takes out that water source. So the snow belt doesn't really build up anymore. But in 2010, no pack ice in the Gulf, right through to March. And Environment Canada did a look at the amount of ice cover in the Gulf, peaked in the sort of early 90s, and has been going down ever since. So 2009, 2010, it was 0. And there are some papers indicating that this absence of sea ice in the Gulf is an impact of our changing climate. So that makes it interesting because glaciers in a temperate climate such as we have are receding at high altitudes. But here we don't have a glacier, but we have a major snowpack, and it seems to be increasing in depth because of changing climate. So it's a little bit different than what you might expect. So what does that snowpack look like? Well, here we'll take you to the monitoring station in here. This is the snowpack. And wow. There is one station that we have here. We were going to try and get up in the snow, but we couldn't get up off the truck. So we have a climate station right there, Environment Canada does. So here I've shown depth of snowpack and months, October through June. Here's what the plot was for the lowland station at the Sydney airport. Up to maybe a half a meter of snow. Really didn't begin till late January, peaked in March, and by April, the snowpack had left. In the lowlands, we get a lot of snow melt, rainfall events, takes the snowpack out. Same year, this site, here's what we got. So up to 2.5 meters of snow, and the reason it flatlines here is it took out the snow gauge, just inundated it. Snowpack starts building up in November, peaks in March, April, and doesn't leave until June. So that becomes quite interesting because now we have to look at how that snowpack melts, its implications for groundwater recharge in the highland terrain, its impact on stream flow in the lowlands. What's the chemistry of the snowpack? Are we getting these acid pulses coming out that some people refer to? A lot of unknowns up in here, so these are known unknowns. Another aspect of changing climate is certainly acid rainfall. We don't tend to hear too much about before, but certainly there we do have our local sources. This is the Lingan coal-fired thermal generating station. But we also have to deal with the concept of airsheds. So here's work done by the USGS showing pHs, mean 1996 to 2000. Certainly a core here in the northeast US and southwestern Ontario. We get the results of it, but we should be in the 4.8 to 5 range here. Unfortunately, there's no precip chemistry stations on the island. There were some back in the early 1980s, and when I looked at that data as a mean annual pH, this is what we were getting. So that agreed with this chart here to the left. So there is some acid rainfall. Some work that's been done by Environment Canada suggests that because of the Clean Air Act in the U.S., sulfate is going down, but the pH isn't rising as one would expect if the sulfate concentrations were going down. Why that's happening, unknown. Impact on Cape Breton's precip chemistry, unknown. One of those known unknowns. Another aspect of changing climate we have to deal with in Cape Breton is fog. This is a fog bank coming in up St. Anne's Mountain. Edge of the Cabot Trail is coming along in here. And it's not so much the fact that we have fog, but it's the pH of the fog. So normal rain around here should have a pH of 5.7. Acid rain is 4 to 5. But in the places where they've looked at the pH of fog, in the southern part of the province, is in the 3 to 3.5 range. So the question then becomes, is changing climate going to give us more fog at these low pHs or less fog? Fog is important here because you can see this is the average number of days with some fog from 71 to 99 across Canada. And you can see that we are, here in Cape Breton, we have 90 to 120 days of fog in here. Only one or two other spots hit anything like that. So certainly fog is important for us. So if you look at the Sydney station data, mid-50s through to present, number of days of fog per year, start off in the 80 to 90 range. There is a general decline into the 70 to 80 range. Whether that's going to continue, how changing climate is going to affect it, how that will affect pH of and impact on the forest cover, unknown for sure. Another aspect of changing climate we have to deal with is the smoke from forest fires. And certainly we've all heard about all the intense forest fires that are going on as the planet starts to dry out. This is a forest fire that took place just around Sydney. Plumes coming off, as you might expect. The interesting thing here for us is what is the chemistry of that smoke. And if you look at the chemistry of fire, you can have acid rain through NOx and SO4 emissions, phenols, dioxin, furans, trace metals, benzenes, toluenes, and PAHs. So if it stays up in the air, for water resources, that's okay, but if it's rained out, then it comes down to ground surface. What is the impact on our ground and surface waters? No one's looking at that. It's a known unknown. Lest you think this is just a local problem, we'll take you to a little bit farther afield, and here is a smoke plume coming out of the big fires in Quebec in June of 2005. So you can see those smoke plumes actually make it all the way over to Cape Breton. And even more important, if we look at 2014 and all the huge fires that have been going on in the Northwest Territories, well, July 23rd, over 400 fires going on in the Northwest Territories. You can see the smoke plume coming down in towards the Great Lakes. By the next day, satellites had picked it up right over top of the Great Lakes, and by the next day, you can see the smoke plume coming right over Cape Breton. So as we start to see more and more forest fires, we have to start looking at the impacts of forest fire smoke on the chemistry of rain and its impact on water resources. Unfortunately, that's a huge known unknown right now. No one's really looking at it, at least in Cape Breton. And finally, in terms of a changing climate, we now have to start to look at dust because, again, as the planet starts to dry out, we're starting to see more dust events. We'll take you on a global perspective over to the Sahara Desert. These huge dust plumes coming off the desert. So 25th June 2012, by less than a month, they could track the plume, NASA could track the plume right over into the Caribbean. And lest you think that those are just aerosol mappings from a satellite. This is what the picture looked like for the Caribbean. The research has been looked at in terms of, this is a positive impact for the Amazon rainforest in terms of phosphates. They think this is a relationship in terms of some of the corals dying off because of the virus and bacteria that are ladled with the dust. This has been tracked coming up in towards the Atlantic provinces. What its impact is unknown, with the exception, we'll just show you this one that happened just this past summer with an apple fire blight. So this is a bacteria that was brought in by Tropical Storm Arthur just this past summer that's hit the apple orchard. So this is something in the dust and in the rainfall that was brought in. So this is an interesting known unknown, but no one is really looking at it. NASA certainly is sending satellites to get a better handle on this right now. Okay, in summary then, talking about a changing climate, what we have to deal with, at least in Cape Breton, is it's a lot more than air temperature, and it's a lot more than just precipitation, but it's also snow, sea ice, fog, air sheds in terms of acid rain, smoke, and dust. A lot of known unknowns in there that we really have to begin to identify. Okay, well that brings us to the last part of the talk, and that is, what do we know and what do we know we don't know about what it's doing to our water? Okay, as we go through this, I'm going to want to be able to show you where these case studies are that I'm going to talk about on Cape Breton. Normally you would show a picture like this, but what we've been doing is to put a lot of our data on a GIS system so we can begin to understand things a little bit more. So instead of just a normal planimetric view, I'm going to lay it on its side, looking from the southeast to the north, from south to north. This is a digital black and white terrain image from Natural Resources. You can see the highlands and you can see the terrain in here. Make it a little more easily to understand, I'm going to overlay a Landsat satellite image on top of that so you can begin to see the actual conditions as they exist. And for those of you who know a little bit about Cape Breton, we'll put in a few spots where you might recognize. Sydney is where we were showing where the climate station was. Okay, so now you've got the background, let's proceed. First thing to consider is that we've done is to divide Cape Breton up into hydrological regions and districts. The concept here is because of quite varied terrain. We've looked at pulling in about 170 to 180 geological units, dividing them into hydrostratigraphic units, about 18 of them, then looking how those are combined and rotated and create hydrologic regions, which then creates a conceptual model of how groundwater will move, how it'll be recharged, and how streams will react. So the pink are the highlands region. They cover about 31% of the island. The canyons in blue cover about 9%. The mountain flank regions, the steep transition slopes, cover 14%. The foothills, massive conglomerates, yellow, cover about 10%. The Atlantic coastal region, massive crystalline rock over till, low topography, cover about 10%. And the lowland region in here cover about 26%. So the concept is we can't just take a look at one stream or one groundwater well and say, this is what it's doing, and apply that to the rest of the island. It only can be applied to the hydrologic region it is situated in. Okay, well, let's take a look at stream flow. We used to have a maximum of 10 stations that monitored natural background conditions, but because of major budgetary cutbacks in the 90s, we're now down to 6 on unregulated natural streams, and the watersheds cover only about 9% of the island. So we have a little bit of difficulty if we want to try and understand stream flow. We'll take a look at 3 here. If we look, here's McCaskill's Brook. The records start in the 70s, go through the present. And if we look at, you remember that 10-year running mean of total precipitation, it's declining during that period. If we look at the mean annual stream flow, this is what we get. The correlation coefficient of greater than 0.9. So what we know is that that decline in annual precipitation on a 10, 20, 30-year cycle is creating declines in stream flow, and one of the results of that for adaptation is that we've had to go in and reevaluate safe yields on some surface water supply watersheds because of this. So as I mentioned before, sometimes as hydrologists and hydrogeologists, we have to look at a decadal scale time frame, not necessarily just the 100-year time scale that climatologists look at. In terms of ice cover, here we're using the Northeast Margaree. So here's the red line is the decadal temperature at Sydney, so you can see it's been going up. And here's the extent of ice cover in terms of number of days during the winter months. So it seems to correlate. Temperatures were down, we had a peak in ice cover. As temperatures go up, our number of days of ice cover are going down. What are the implications for ice jams, for fish in the streams, for stream flow? Unknown at this stage. So it's a known unknown. Another complicating factor we have if we're trying to understand the impact on stream flow by that changing climate. Here's the Northeast Margaree River Canyon, Cape Breton Highlands in the background, and over here on the left, the broad flat alluvial floor underlain by sands and gravels here. Problem is that we got hit in the highlands with spruce budworm infestation. If you look at the amount of damage that was done by the spruce budworm, this is from Natural Resources, and this particular watershed is up in here in the highlands, so you can see that by 74, 75, 80, 84 it admitted. But it did a tremendous damage on the boreal softwood forest that was up there. As a result, the pulp plants went in and did massive clear cutting up there. So the results of that clear cutting have to be taken into account if we're trying to separate out that impact from any change in climate. So if we look at the records, this is just above the Northeast Margaree River gauging station looking at the canyon and the highlands area in the back. If we plot up the stream gauge station, mean annual stream flow, now this is that precipitation trend, 10-year trend. If we plot the stream flow, we see that the increased precipitation has created an increase in stream flow. But we also have to account for all this spruce budworm damage, and massive clear cutting happened about this same time. So if we're trying to separate out what's going on in the stream flow from the precipitation, we have to try and understand the impact of this spruce budworm deforestation. Just one of those complicating factors, makes more known unknowns. Another aspect that we have to deal with is the remoteness issue. So this is the Clybourne River Canyon. For those of you who enjoy golf, this is the Cape Breton Highlands links. You're looking at the Cape Breton Highlands Park in here. Highlands area in the background. Part of the problem with this remoteness issue is that up in the Highlands, we have only one climate station. We really don't understand all the climatic things that are going on up there. But most of our people live in the lowlands. And a lot of our monitoring is done in the lowlands. Problem is you can get big storm events going up in the highlands that never hit the lowlands, and we get these massive storm flows coming down here in the Clybourne. Breach can't get through the small bridges, so they breach over top of the road. So the perception then becomes, this is due to changing climate. Well, it could be just as much due to we just don't know much about what goes on in the remote areas of the highlands. This may just be a normal event. The impacts are created by just the fact that we put man-made infrastructure across the stream valley. So we have to separate out a remoteness issue and a perception issue. Channel morphology and sediment transport. In order to understand that, I'm going to lay in the superficial geology of Cape Breton. And we're going to take a look at 3 different things. Actually, 4 sites. The thing to consider here is that if we're looking at the impact of a changing climate on streams, we have to look at how it's changing the morphology of the channel and sediment transport, and neither one of those are being picked up by any government agency monitoring program. So these are just more conceptual ideas on my part. We have different types of channels. We have bedrock channels with bedrock terrain covering about 30% of the island. And if we look at Halfway Brook there, this is what it looks like. So these are bedrock line channels. If we get increased stream flow, it's really not going to change the channel morphology that much. No sediment being transported down here. Groundwater stream interaction is going to be interesting, trying to understand that in a bedrock line channel. Nothing being really done on that at the moment. We also have channels that are carved in till. Glacial till covers about 50% of the island, 54% of the island. Look at McCaskill's Brook as an example. These are wide, shallow channels. They're not down-cut deep. And the reason being is that there's pretty coarse boulders and cobbles in the till. The channel winnows out the fines, leaves the coarse stuff, forms a lag at the bottom of the channel, can't be moved by bed load transport. So it forms sort of an armoring across the bed. So in this situation, we have the flow in the channel with a low permeable till underneath and a fractured permeable bedrock beneath that. So what is a groundwater stream interaction here? If the channel can't cut down into that more permeable, shallow bedrock, it's then governed by the till. How does that groundwater stream interaction take place in a situation like this? And in this case, the morphology of the channel isn't affected too much because we had this lag pavement. Known unknowns. But the real interesting part comes in the sand and gravel channels, which covers about 4% of the island. Take you to two places here. First of all, Glenbrook. So these are large alluvial valley channels, large amounts of sand and gravel. With the increased flow that we got because of that increased precipitation, peaking in the sort of late 80s, early 90s, a lot of undercutting going on, good sinuous channels, bringing in the riparian zone. It moved a lot of gravel down the streams. And so for groundwater stream interaction, it becomes very permeable bed. But there are other areas where we get a lot of sand and silts and clays in it, which would restrict groundwater stream interaction. How these play out, how these change in the channels, unknown. But it creates another interesting aspect, and that's presented by the Northeast Margaree River. It also exhibits the same conditions. And the first indication there was something changing is this is a major salmon fishing stream. But the salmon fishermen were noting that a lot of their salmon pools were being inundated by gravels. And what we think is happening is, if we look down here, because of the spruce bloodworm damage peaking at the same time as the high precipitation, large flows going down eroded a lot of gravel out of the banks and put it into transport in the bottom of the river. But then the trees grew back, precipitation decreased, so the big flows to move that gravel down the channel decreased. So that all that gravel that was in there is still in transport. And you can see large mid-channel bars in here. And so if we go here and look across the channel, you can see these big gravel bars, the large woody debris that's being brought down. And what's happening here is that it's decreasing the ability of the channel to handle a same peak flow, because the gravel is filling the channel up. So if you go to the same spot in almost a 1 in 100 year event, you can see massive floodings, big LW, large woody debris banging into the bridge here. So this becomes, as one person called, a memory effect. This is a memory effect, which means something that happened 20 to 30 years ago is now just moving down the channel. It's creating more flooding. So is this an impact of a changing climate with altering stream or intensity, duration, frequency events, or is this something due to a memory effect that happened 20 or 30 years ago? So if we want to understand the impact of a changing climate, we have to start separating out a lot of these known unknowns. And as I said before, channel morphology, sediment transport, whether suspended or bed load, is just not something that's being monitored for. Another aspect is, well, that acid rainfall we talked about, has it impacted stream water quality? Now, take a look at two streams. And the reason for that is we have two different types of stream chemistry on the island. We have clear water systems, as represented here. This particular one, we have a moderate frequency sampling program going from the mid-90s to present at a once per month frequency. The blue is total dissolved solids, shown here, 2, 3, 400 milligrams per liter. The red is pH, ranging between 7.2 and 8. There's no real good trend that's changing here. And the question then becomes, statistically, is there some way, how do we get a handle on if there is a change? Do we do means, modes, medians, standard deviation? But in this system, what we can also do is trying to develop a rating curve. So if we compare total dissolved solids with discharge, a log-log plot, we can start to develop a nice rating curve And this is a better way of trying to isolate if there is a change going on that wasn't a natural change. Another aspect that I really haven't heard too much about, but we have information on this particular stream, is bacteria. If the place is starting to warm up, one would tend to think that the normal bacterial load in these streams might change. So same monitoring frequency. The blue is total coliform bacteria. The red is fecal E. coli bacteria. Lots of fluctuation. Certainly in the summer months, water temperatures are warmer. We're getting peaks, and in the winter, they drop down. Again, what statistical method do you use to pick out whether or not there is an anomaly in there? I thought maybe if we plotted against discharge, total coliform against discharge, no way, just a scatter plot. I thought, well, maybe it's water temperature. Water temperature, well, you're starting to see something here, but boy, it just isn't a good correlation. But the question then becomes, as we do have some data in here, but the question becomes, how do we statistically analyze this to detect a trend created by changing climate? A known unknown. We do have clear water systems, which what I showed there, but we also have a lot of colored water systems because of the vast amount of wetlands we have. In these colored water systems, the chemistry just becomes a major problem. We try to create a discharge versus total dissolved solids rating curve. Whether it's calculated TDS or whether it's analyzed TDS, there's just no rating. Our ion balances become quite large because of the high total organic carbon and color, and this becomes even more problematic as to how you statistically define a change in a colored water system. And it's these colored water systems that could be impacted because wetlands are thought to become one of the first indicators of a changing climate as they dry out, then more organics are flushed down the system. Another big known unknown. Lakes. Well, lakes are shown here in red, and we have about 17,800 of them on the island, covering about 3% of the island. There are no lakes being monitored by the provincial or federal government monitoring programs. There are some lakes that are being monitored on an irregular basis by municipalities. And there are a number of lakes up in the Cape Breton Highlands Park, and the parks people are monitoring some of them. We'll just take a look at two. One is one that we've been monitoring on a low frequency over here in Lake Ainslie. This is the largest freshwater lake in the province. We have a very low frequency manual monitoring on this. We just try to pick up the highs and lows, 2002 to 2014. No real trend going on there like the surface water stream flows. Well, what about the chemistry? Well, once per year chemistry, pretty low frequency monitoring. We look at total dissolved solids from 2003 to the present. This is what we get. If we look at pH in red, this is what we get. So there seemed to be a bit of a trend going down here, and then it seems to flatline. But this is a pretty low frequency monitoring program. And when you're dealing with low frequency, again, statistically, how do you detect an anomaly in there that says something is going on? Anybody who's got some ideas, be glad to hear them. The other reason I showed this slide is you'll see quite a green discoloration in here. Well, there were 3 big algal blooms in this lake, 1990, 2009, 2010. Nova Scotia Environment did a limnological study. Back around in here in the early 90s, they found this was not due to eutrophication. So what is the reason for these algal blooms? Are these natural? Are they due to something changing because of a changing climate, and we're going to see more of them? There's a lot of recreation going on in this lake, and as soon as these algal bloom hits, you can't get in the water. The other lake I'm going to take you to is called French Lake. It's up on top of the Cape Breton Highlands Plateau in the park in a taiga forest region. And just when you think you might understand something, Mother Nature finds to change that idea quickly. So we'll take you down to this spot right here and take a look under winter landscape. So the Highlands Park people have been looking at the number of days that the lake has been frozen. They started their records early in the 2000s up to present, and this is the trend that they got. So less and less days frozen each year. That would tend to agree with a higher and higher temperature being felt in the winter months. That seems to make sense. Whether you look at the few records we've got at the one climate station in the Highland Plateau and look at the number of days the temperature was below zero or freezing, we get this trend, just the opposite. So there's something else going on up in here. What it is, we have no idea. So it's another one of those intriguing known unknowns. Groundwater. Okay. There are a number of issues in groundwater we're going to talk about. So let's load this up. These are all the well logs, 14,800 of them that Nova Scotia Environment have for the island. In terms of looking at the impact of rising sea level and seawater intrusion, what I did is to ask the system to assess how many of those well logs are within 1 kilometre of the coast. So 55% of them are that way. So yeah, rising sea level, saltwater intrusion is going to be certainly an issue for us. These are the 7 groundwater observation wells that Nova Scotia Environment now have. We had an issue back in the 90s. We had quite a number, but because of major budgetary cutbacks, they were all eliminated. To their credit, Nova Scotia Environment has now started in the last 5 years or so getting them back online again and changing them from chip chart recorders to automatic data loggers. So the good data is starting to come out of here now, but those big economic downturns certainly do a major problem for monitoring. Fortunately, there are a number of private sector organizations that also have been doing some monitoring. So we're going to take you to this location here. So this is data courtesy of Nova Scotia Power Corporation. So we've been monitoring manual levels about 10 to 15 times per year from the early 90s right through to present. And this is in a shallow bedrock monitoring well. So it's only about a 5-foot saturated zone right in the top of the bedrock, so it should record the very first signs of any change. So you can see we get nice frequency going on here, certainly the big peaks in the spring and fall recharge periods and the summer recessions. No big major trend. And if we look at the water levels at the end of each water year, end of September, early October, there's been no declining trend like there was in surface water. So groundwater reservoirs don't seem to be impacted by that change in declining precipitation. We can note, however, during what was called the Ada drought that we experienced, which crossed all of Canada, started in 1999, went through to 2004, but peaked in 2000, 2001. You can see we had very low summer recessions, but we always had the fall and spring recharge to bring us right back up. Interestingly enough, no major droughts that have been defined climatologically, but we still do record some big lows in here. So what we've been telling people is that if you have a dug well or a shallow bedrock well, you're probably going to experience some pretty low summer conditions. That may be an impact of a changing climate. Well, what's done? Are there any changes in that, in the chemistry of that groundwater? So same well, the blue is total dissolved solids, the red is sulfate, the green is pH, going from 91 to present. A lot of fluctuations, but no major change, no sign of any change in the chemistry in the shallow bedrock. And this would be for a semi-confined sedimentary bedrock just below a till cover. We also have a monitoring well that we have in a water table sand and gravel aquifer, only about 2 to 3 meters saturated, unsaturated zone. We've got records from 88 to present, but only on a once per year low frequency sampling event. Again, blue is total dissolved solids, red is pH, green is chloride. Can't really detect any major trend, and it should be this well, if anything, that would show a alteration in water chemistry if there was something going on between precip chemistry and groundwaters. So that's a known. However, we also have karst on the island. Approximately 25 to 30% of the island is underlain by units that are susceptible to karst. That ranges from marbles to big evaporite units from gypsum and hydrite and salt. This particular one is a limestone unit, and here we can have hydraulically inactive karst. So they've just pulled the till cover off of this, and you can see the till embedded down into what used to be a paleokarst. But just adjacent to this, within a couple of 100 meters, you can have hydraulically active karst. So the question comes then, how in the world do we try and get a handle on what's going on with karst? The concept is that if groundwater levels are declining because of declining precipitation, you remove the hydrostatic pressure and you could get collapse of sinkholes and more sinkhole development. As an example, we were monitoring this one, and this is an aerial photograph in 1985. All of a sudden, quickly, flew it in 2010, the sinkholes had collapsed, massive amounts of mud going down here into the adjoining wetland, changing the water levels and destroying the tree cover in the wetland. So, is that a natural phenomenon? Is that something that's going on because of a changing climate? It's a known unknown. And how would you monitor that in a groundwater system to hit those hydraulically active karst zones? Well, one way I've been trying to get a handle on is that we have a small watershed, less than a square kilometer, hydraulically active karst. This is data courtesy of Georgia Pacific, and we've been monitoring flow and chemistry on that over about 10 years now at a once per month frequency. And interestingly enough, if you plot up total dissolved solids versus discharge, you're starting to get a nice rating curve. So maybe that's the way we get a handle on changing conditions in karst. That's possibly a known unknown, but a lot of known unknowns at the moment. Sea level rise, saltwater intrusion. This becomes quite an interesting aspect for Cape Breton, and I have to now begin to bring you back and look at a big time scale, because 9,000 years ago, the ice left Cape Breton about 9,000 years ago, our sea level was about 50 meters below where it is right now. So this was outlined in green where Cape Breton Island was. It was joined to the mainland and joined to PEI. With sea level rise, as the glaciers receded, we had isostatic movement, which is the movement of the ground surface up and down, and eustatic movement, which is the movement of sea level up and down. Those combined by 6,000 years ago created this form of Cape Breton Island. So we were still linked with the mainland, but not PEI. But at 6,000 years ago, water levels reached a high enough level that they crossed a sill here and started to flood out the internal portion of Cape Breton. So what we now know as the Bredora Lakes originally were just dry land, a few freshwater lakes, and now they're all flooded because of that sea level rise. And that's moved up and created all sorts of major estuaries in here. So in terms of sea level rise, we've seen a lot of sea level rise already in Cape Breton and have to deal with the impacts. There's another part of that. This is the northern tip of Cape Breton, and that is the last interglacial was 125,000 years ago. Temperatures were approximately 2 degrees centigrade warmer than they are right now. Sea level was therefore higher, and because it stayed at one spot, it created a wave-cut terrace, which you can see down there. And so this is where sea level was 125,000 years ago. So let's take you down to the beach there to see if we can make some sense of this temporal view of how sea level has impacted Cape Breton. There's the sea-cut terrace 125,000 years ago. Let's create a little bit of a graph here. So right now, the natural sea level rise in Cape Breton, combination, it's half due to land sinking and half due to sea level rising, is about 0.36 meters. The International Panel on Climate Change, 2007, forecasted 0.2 to 0.7 meter rise. That would be added on to our natural rise. By 2009, they changed their estimates to 0.5 to 2 meter rise. Now the latest is 0.26 to 0.9 meter rise on top of this.
And Fred, over what time period are these rises projected to occur?
Out to 100 years. That's a good point. So those are what the rises are forecasted to be out to 2100. However, there are a number of people that say if we have abrupt change, so this is if all the Greenland ice sheet melted and or those major ice sheets in Antarctica melted, the forecast is for a 5 to 7 meter rise, which interestingly enough would put it right back to where we were in Cape Breton 125,000 years ago. Now on top of that, we have to add in storm surge, because if we're getting more storm surges by increased hurricanes or nor'easters, then interestingly enough, right now, the normal storm surge is said greater than 3.6 meters every 40 years. By 2100, they're forecasting that same once a year, and greater than 4 meters once every 10 years. Now, on top of that, we have to deal with tsunamis. Now, we are in a passive continental margin. We don't have major earthquakes, but we do have steep submarine slopes going into the Cabot Strait north of us or in the continental shelf south of us, and one of those back in the 1920s created a 7-meter tsunami wave coming into Sydney. So if we're talking about a changing sea level, we have to accommodate all these factors. So we asked the GIS system to say what areas would be inundated for a 10-meter rise, and what was shown here in sort of a light blue. We have one well that we've been monitoring. It's an open bedrock hole, about 30 meters of saturated thickness. It's about 0.5 kilometers from the coast. We've got a data logger in it. So from 2004, we're seeing this trend in water level, going up at about 0.06 meters per year. And interestingly enough, that's about equivalent to what we see with the tidal gauge stations. And if we plot up TDS in blue and chloride in red, you can see that we're gradually starting to see a chloride going from, about a little over 10, and now we're up about 20 to 25. We're starting to see some bit of saltwater intrusion coming into this coastal aquifer. Impact of that on rising sea levels of communities becomes quite important. This is the community of Eskazoni. You can see if you had a 10-meter rise, most of the community would be inundated. The reason I use this as an example is that there's a hydraulically active fault zone coming down the transition zone, which we've developed a groundwater water supply in. So what would be the impact of just saltwater intrusion in there? Well, we asked the GIS system to say, where are all the communities on Cape Breton Island? These are all in red. How many of them would be impacted by a sea level rise of 10 meters? 72 of them. A number of those, like Eskazoni, are on groundwater supplies positioned close to the coast. So this intrusion of salt water into a diverse set of hydrologic settings and impacting those groundwater resources becomes quite critical for us. But there are a lot of known unknowns because a lot of these in different hydrologic settings, and there are no specific research systems set up by the governments to try and address how that is occurring right now on the island. Another aspect of groundwater is springs. So springs are not part of a government monitoring program. For about the last 5 years, we've worked with another hydrogeologist down in the mainland who's been looking at springs all over Nova Scotia, and we've added the ones that we know about in Cape Breton. There's about 160 of them shown here in blue pins. Right now, we're about over 200 of them. I'll take you to this particular one in here. So this is Kelly's Mountain. Steep transition slope, hydraulically active fault zone. This is where we tend to see the big magnitude springs. In this particular case, we've got 6 springs over about a kilometer distance, anywhere from 500 liters per minute to about 7,000 liters per minute. These would form really good monitoring points. We have a very, very low frequency, once every couple of years, where we go in and look at these. As I said, none in the government monitoring programs. And the interesting thing is that there can be, where other areas, say in the U.S. or in Europe, have looked at springs, the other thing they're concerned about is what unique ecosystems are around these springs that have to be protected, and what role do these springs form in creating base flow to nearby streams that then have an interesting aspect in terms of protecting salmonids, salmon and trout. One of those known unknowns. Wetlands is another aspect of groundwater that we want to take a look at. There are about 14,000 of them on Cape Breton Island, shown in yellow here, cover about 8% of the island. Certainly quite a number of them occur up here in the Taiga Forest region, in the Cape Breton Islands National Park. Although the blue pins indicate that there's been some assessment, there's no long-term monitoring on any of them, except for some in the Highlands Park, and we picked up one here that we'll take you to right now, called the Big Barren. And this is here. Aerial overshot, this is about 380 hectares in size. Our monitoring site is just over here, and the reason we chose this was it's a major wetland. It's in the Highlands area, which is remote, that we never, there's not a lot of data on. We're going to take you to this spot down here, and the reason that we chose it is this is a watershed divide. So this particular stream leads down into the Middle River watershed, and this one leads down into the Baechler River watershed. So we're really looking at the headwaters of two major streams leading into the Bedore Lakes. Here we've got 4 monitoring wells in here installed in the peat. One of them, we installed a data logger, and so we have records from 2010 to 2014. At least we have something to start with. Here are the records for a summer season, so we can certainly see a lot of rainfall events occurring in here with nice recessions. The red is the temperature, so it's going up to about 13 degrees C, and then dropping down in October to about 8.5 degrees C. Here, the unsaturated zone is less than about 0.3 of a meter, so we've got a really high water table in here. And one of the reasons, as I mentioned before, we were monitoring these wetlands is that wetlands should be the first indicator of a drying out. So the indication there would be is that drying out, we're going to start to see a decline in water levels, and because of that, we get greater unsaturated zone, more organics being pumped down the system, a change in vegetation in these areas, and how does that impact the streams that these drain into? We were wondering whether or not our data logger would last during the winter months, because most people said these big barrens, the snow cover just gets blown off them into the trees to the sides, so you get a good frost buildup. So we thought, well, these monitoring wells are only about 2 to 2.5 meters deep. Maybe it's going to freeze solid. So this is the past winter, and you can see we're getting snowmelt events in here. Temperatures drop down to about 2 to 3 degrees, about 3 degrees, and then come back up again. So we're getting at least some good groundwater inflow probably coming up from the bedrock. And this is what you would call a graminoid fen marsh pool system. So far, we haven't seen any indication of a drying out, and we haven't seen any indication of frost buildup. We're starting to see some indication of what impact that will have on stream flows and organic load and color load. With a lot of some known knowns, but a lot of known unknowns. Groundwater stream interaction. As I mentioned before, the big one takes place in these big alluvial valleys. This is data courtesy of Georgia Pacific, and part of the stipulations for opening up the mine was to really begin to look at develop a salmonid management zone. A lot of people know salmon are in decline. They want to begin to understand, well, is this something that's going on in the watersheds or out at sea? So there's 2.5 kilometer zone we've been looking at for over 10 years, about a 2.5 kilometer reach, records from 1998 to present. So we monitor stream flow on a manual basis once per month. We've installed some monitoring wells here adjacent to stream. We do head levels in here, head levels in the stream as well. If we look at head levels, the blue is the water level in the stream. The red is the water level in the shallow bedrock in the sand directly beside the stream. And we have a 30-meter deep sand and gravel infill bedrock channel here. So at roughly 25 meters depth, this is the water level. So you can see we're getting a good groundwater discharge zone where groundwater moving up from the deep to the shallow to the stream. The green is just the discharge that we've been monitoring in the stream. So far, at that level of frequency, we're not seeing any major change. We're seeing good groundwater stream interaction. But again, statistically, how do you deal with this? Should we add data loggers in? What are the methods to get a better handle on this? Good questions. One of the interesting things we found is that this is not just a static system where you can select one site, put your wells in, measure the stream and say, that applies to the whole rest of the valley floor. Because what's happening is, again, because of that big bed load transport system, now this is in another stream that we're also looking at, because of the big bed load transport that's been going down these streams, they infill the channel, in this case, right up to the top of the channel, and the stream flow just becomes totally influent. Just goes totally into the groundwater system. And then about 500 meters down gradient, pops back out again. So how do you deal with the groundwater stream interaction in here? And this bed load gets pushed right back out into the floodplain, so the floodplain is building up. The level of the floodplain is building up. So, where do you call ground surface? It's constantly changing. Another aspect of this, it's these type of channels that just the beavers love. So we get these massive beaver channels built up, huge headwater ponds in the back. That completely changes head levels in your stream, changes groundwater stream interaction. And when these dams actually break, you get all sorts of fine-grained sediment deposit in here which sort of seal off the bed, even after the dams have been breached. So how does that impact and change groundwater stream interaction? Some good known unknowns. And finally, another aspect in these big systems, the province is really starting to take an interest in vernal pools now, especially as they start to highlight impacts on special ecosystems. So where we've seen these are in the floodplains, where they're old abandoned channels that have been cut through the floodplains. But in the spring and the fall, the groundwater table builds up, floods them out, and in the late summer, they're dry. How do we get a handle on these systems and link to the biology of the ecosystems in these pools? Something that's not being looked at, it's just a known unknown. And the final aspect of groundwater we're just starting to get into now are estuaries and baryshwas. As I mentioned, we're in a coastline of submergence, so we have these big estuaries built up along here, massive systems. But we also have what are called baryshwa ponds in the Bedore Lakes. I'm going to layer in the bathymetry of the Bedore Lakes, take a look at that area there. So the deep blues are the deepest parts of the lake, the yellows and orange are the shallow. And we have a number of these ponds built up along the shore of the lake, 400 of them, as a matter of fact. And that's what a baryshwa pond would look like. So you have streams coming in, but you have these large baymouth bars. Sometimes they're open, sometimes they're closed. But these systems are considered nurseries for a wide variety of aquatic aspects, and the First Nations are quite interested in them. The other aspect from a management point of view is you can see there's a lot of buildup along the shores of it, and sometimes people decide they actually want to build right on the bar itself. And sometimes these bars, if they're closed, they get bad smells, and of course people then want to break through the bars, create more flushing. But what impact does that do in terms of nurseries? So the managers, the provincial and federal managers, need to know what's going on inside these. So for us, this becomes important because we're working with a team, and our aspect is looking at groundwater interaction with the ponds, and then you also have biological aspects, you have the oceanography aspects, sediment transport aspects. It's quite an interesting project. Certainly with climate change, the impact is, well, you may have had a closed bar at one point. So this was a particular bar, took a shot in the 1980s, but with a little bit of sea level rise we've got so far, it's starting to inundate. It's now a completely open system. So for a lot of these systems, it becomes interesting in terms of can the bar build up because of ocean dynamics and sediment transport as fast as sea level rises? And what does that increase in sea level rise do to groundwater seawater interaction? Okay, well, I hit you with an awful lot in a short period of time. Now, what can we say about conclusions? Well, if you're anything like me, if you want to start thinking about stuff like this, what you really want to do is go to the nearest liquor store, buy yourself a couple of cold beer, and go out in the woods to your favorite spot where there are no cell phones, there's no email, there's no voicemail, there's no Twitter, there's no nothing. It's just nice and quiet. You can crack open a cold one and think. So this is where we go. This is up in the headwaters of the Northeast Margaree River Canyon, embedded way up in the Cape Breton Highlands. You're looking about 300 meters down in the Northeast Margaree River on just a beautiful fall day. First conclusion, climate is changing, whether it's natural or man-made, it's changing. And its impact on freshwater resources is changing through a variety of space and time scales while integrated over multiple disciplines. Second conclusion, we do have some known unknowns, but we have a hell of an awful lot of known unknowns. And we don't have a lot of monitoring that's going on, there's not a lot of research, and there's not a lot of that thing being supported financially. So we may just get to the stage where the best we could do is identify the known unknowns. So the real problem then becomes is management. If you can't manage what you don't understand, how do we get into adaptation? As hydrologists and hydrogeologists, how do we advise the decision makers to adapt if we have this many known unknowns? Do we say go with the precautionary principle and just assume worst case conditions? The cost might be that might be a hell of an awful lot more than just putting a lot more money into science, monitoring, in beginning to understand what's going on. Anyway, well, thank you very much for your time.
That was great, Fred, and your photos, by the way, are amazing.
Thank you.
Your love of Cape Breton Island is very apparent in your photos.
Let's hope that gets some people interested in coming up here to do some research.
Yeah, I was going to say it's really going to. If people haven't been to Cape Breton Island before, when they see your photos, they're certainly going to want to go there. Now, these data collection activities, this research that you've done over the years, I just wanted to clarify. This is, for the most part, this is work that you've done on your own, just out of your own personal interest, and you've assembled these data sets from various sources and then analyzed them on your own. Is that correct?
Pretty much correct. For those of you who don't know, my wife is also a hydrogeologist. So between the two of us, our kids are gone, so we have all sorts of time at nights and weekends, and we can go here, there, and everywhere and collect all the data that we've been able to, and that's been interesting as well, because it's taken us about 15 years to go find where all the data are, because they're stored everywhere, in universities, in consultant reports, in thesis, in provincial government, municipal government, federal government databases. And trying to collect all that and pull it together was a major job in itself. Interestingly enough, there are a lot of private sector companies, as I've mentioned here, Nova Scotia Power and Georgia Pacific. We've been working with them on their monitoring program, so they're the ones that have been paying for it. But to their credit, they've allowed us to use the data to begin to understand what's going on. And then we've also put our own money into monitoring a number of the sites as well.
That's excellent. And this is work you intend to continue for?
Yep, absolutely.
Excellent. Now, Fred, one of the slides you showed quite a ways back was for hurricanes and thunderstorms.
Yes.
And I was interested. Now, we often hear that hurricanes are increasing in frequency. I think that your data showed that was not necessarily the case, and maybe that was just not the case for Cape Breton Island, or was that data related to the origin of hurricanes down south?
Well, that data set came from Environment Canada, and they've been looking at that related to the hurricanes that hit the east coast of Canada, and they were trying to show that there are cycles in hurricane activity. We are at the moment at no way greater than what we've seen back in the 30s and 40s. Whether that's going to increase, it's one of those known unknowns. One of the interesting things in talking to the hurricane people last year was one of those massive dust storms that came off the Sahara and blanketed the southern Atlantic. The hurricane prognostication was for a very active hurricane season, but because of that massive dust cloud, it cooled off the southern Atlantic and really reduced the number of hurricanes. So when you talk to the hurricane specialists, I think they'll say, we think they should increase because the planet is warming up. There could be an awful lot of other factors that we're just beginning to see that are playing into this. So when you get to that stage, I just talk to the hurricane specialist inside Environment Canada. They've got a lot of knowledge.
Right. Now, I like the way you broke it out into unknown knowns and known knowns. Now, maybe you could just summarize the known knowns for us and say what kind of confirmed changes did you see on Cape Breton Island in terms of long-term effects of climate change?
Well, when I give a talk, not quite to this technical level, but when I give them to NGOs or sometimes planners that are asking, well, how do we adapt? I guess the bottom line is this. Climate is changing. It could be natural, it could be man-made. Don't worry about wondering whether it's man-made or not. Just assume it's changing, and you better start adapting now. Second point is we're seeing increased temperatures, and we're seeing decreased total annual precipitation, and we're seeing less snow in the lowlands. The impact of that has been decreased mean annual stream flow in the lowland regions. So if you're on a surface water supply, whether it's a house or whether a municipal surface water supply, you really need to better understand what the safe yield of that system is. And a lot for the surface water supplies around here, the safe yields were calculated back in the 50s and 60s. So we've had to go in and actually reevaluate those safe yields. Another twist in that is that not only do you have to reevaluate the safe yields as to how much water is there, but because of the interest in salmonids, salmon and trout, the federal government, Department of Fisheries and Oceans, are starting to say, oh, you have to leave more of that water in for salmon and trout now. So the impact is then we've got less water in the streams, and now you have to divvy it up between the salmon and trout as well as what's available for man. So really start looking at your surface water supplies. In terms of groundwater, the groundwater system in the shallow bedrock aquifers in the lowland areas don't seem to be changing. We haven't been able to notice a big change as with the streams. However, if you're in a dug well or a shallow bedrock drilled well, you're probably going to see the place dry up during the summer. You may not have enough water. If you're into a deeper drilled well, going down like, say, 50, 100, 150 meters, you may not notice as much of that drying out in the summer. We're not noticing a change in chemistry in the shallow bedrock groundwater, so that doesn't seem to be an issue. For those wells really close to the coast, even in the deeper wells, you better start taking a sample once or twice a year, taking it to a lab and just analyzing it for chloride, just to see if you're starting to see an increase in that. And finally, for those, we have a lot of people, especially people from way coming in, want to build right along the edge of the Vidora Lakes to have water frontage, or build along the edge of the shoreline of Cape Breton to look out across the ocean. But a lot of these people build right down at the shore and right down at sea level. That's not a wise move because of what could happen with those sea level changes that we're talking about. And as part of that, when I talk to people, I say, look, the best science can offer right now is a 1 to 10 meter rise in sea level by out 2100. So it's up to you to determine how much of that risk you want to take. Where do you think you should sit in it when you build your house close to the coast? The decision right now is yours, because there are no planning restrictions that will supersede what you want to do. But if you look at what happened in the States with all the hurricanes coming up and the insurance company saying, no, we're not going to insure you anymore, it might be that in the future it's the insurance companies that make that decision for you and not you. And finally, the other aspect of that is when I talk to people, they think, well, that's the water level rise. No, the water level rise, even at 5 to 6 meters, it's not going to get to the stage where it's going to flood my house. But then we have to point out to them, well, if you're out there, you're on your own well in your septic field, and those are below grade. Those are the first things that are going to get wiped out long before your house gets flooded. So keep that in mind. And usually in those situations, your well is behind your house and your septic field is in front of your house, between your house and the water. So the first thing that might get flooded out with a rise in sea level is your septic field. And what use will your house be if you can't get rid of your wastes? Or what use will your house be if you don't have a water supply? So those are sort of the known unknowns that I've been using to talk to people about how to adapt to this stage.
Sobering thoughts. We had another excellent presentation a few weeks ago by Dave Bout, Fred, and I know you indicated that you had listened to Dave's presentation.
Oh, yeah, it was a great talk.
Could you compare some of your results with Dave's? I mean, Dave's main conclusions, which I think among them were that precipitation was increasing and several other conclusions too. But could you compare against some of Dave's main conclusions? By the way, I'll just mention that Dave's presentation related to the northeastern U.S., so not that far from Cape Breton. As the crow flies, probably several hundred kilometers.
Right. And I think for those who are watching this, it would be good to listen to Dave's talk. And the thing that struck me where the difference is. I had assumed that the northeast U.S. is in close proximity to Nova Scotia and Cape Breton. We're under the same climate regime, one would think, and we're in the Appalachian origin, so we're in the same sort of geological conditions. They have more a hardwood forest where we have a combination of Acadian hardwood, boreal softwood, and taiga. So the forest region is a little bit different. Same sort of topography. So I was interested certainly in watching what David had to say versus what I was seeing. The interesting things that popped up in my mind were, one, he was seeing this rise in precipitation and looking at those trends, and that's what the long-term trend was looking for. Whereas what I was seeing here was a difference. We were declining in precipitation. The other interesting aspect was that in the northeast U.S., it was just amazing the data sets they had for surface water, groundwater, climate. Like someone had really been thinking. They had integrated monitoring programs, good high-frequency events. They could really begin to start to do some statistical analysis on it, pull things out, and start to see the impact of the changing climate. We just don't have that here. And the third thing was, since we don't have it here, I was hoping to be able to draw on what David had because we were so close. But given those changes in the climate that he's seeing versus what we're seeing, I just don't know how close we'll be able to pull what David has and bring it up here. I think we have to have a long talk with David over a couple of beer on that one. So,
you mentioned a hydrogeologist on the mainland that you're working corroboratively with on the spring research. That's right. Heather Cross?
Yes. Mm-hmm. And to her credit, I don't know, it was about 5 or 10 years ago, Heather decided on her own to look at and document all the springs in Nova Scotia. So we've been helping her out with identifying the ones in Cape Breton and adding to her database. So I just keep tabs on the ones in Cape Breton that I've shown there. So we go around and get GPS coordinates on it, do a flow, and at least do conductivity and temperature on them. For the bigger ones, we've sampled it a bit more frequently. One of them we put a hobo temperature logger in to try and see how the temperature is changing. Some of them we have full chemistry on. And that was one of the things that got me into it was that we were over on a field trip with the IAH conference when it was held in Munich. And on one of the field trips we were going around, and they have just a tremendous groundwater system, but a major part of that is monitoring springs. So we've been trying to push to get some springs into not only the Nova Scotia groundwater monitoring program, but we're also working with Parks Canada in terms of having them start to monitor springs up in the Highlands Park as well. So we think bringing springs in could really begin to help us understand systems, and if people are interested in ecosystems and what are unique and fragile plants, then they may be around some of those spring systems.
Well, I know you're going to have I know people are going to have a lot of follow-on questions here, Fred. Would you be okay if they email you directly?
Sure, not a problem, by all means.
And so could you provide your email address? I don't recall whether it's on your title slides.
No, it isn't. So it would be Fred.Baechler, BAECHLER, at EXP, as in Peter, .com. So Fred.Baechler at EXP.com.
Thanks, Fred, and thank you for showing the amazing photos and giving us the details of the work you've been doing on your own over the last several years. It's a really interesting data set that you've assembled, and I'm sure you're going to draw lots of tourists to Cape Breton Island with your photos.
Thank you, and thanks to you, Mark, for getting in this webinar series. I mean, this was a great concept. We've had so much problem in the past trying to bring hydrogeologists together in Nova Scotia because we're separated over such a wide area, but this concept of webinars, so people just go on at their own time, great idea, great concept. Thanks.
Well, thank you very much. And people won't know this if they're not from Nova Scotia, but I'm in Halifax, you're in Sydney, but we're still 500 kilometers apart. So
yeah,
so we don't get to see each other very often, but we will be having a face-to-face seminar series starting up this fall, Fred. So hopefully you and Lynn can make it up to Halifax for some of those talks.
For sure, as long as you're bringing the beer.
The beer will be there, my friend.
Oh, dear.
And I hope to see you soon.
Indeed. Take care.
Talk soon. Bye.